So we got through pretty much most of the day here without having to deal with an AI thing, but here we go. So I apologize, it's only 5 minutes. We'll go ahead and get started. So what I want to talk about is classifying point clouds with 2D computer vision methods. For people, in case you don't know what a point cloud is, earlier Zan showed some point clouds over where she was showing the roller coaster on there. It's kind of like that, but what I'm talking about here are point clouds that are collected from a vehicle, a moving vehicle, or maybe somebody carrying a backpack with a LiDAR sensor on it. Unfortunately, I don't have a picture of the LiDAR sensor in front of in my slides, but you could think of it as a cylinder that spins at about 10 hertz, and it has about 64 channels vertically. And what it ends up doing is creating this. You can actually visualize the point cloud as a panoramic image, like what you see here. This comes directly from the LiDAR sensor. It's an OS164 made by Ouster. And you can clearly see things in it. There's also a lot of information in that picture. There's 3 different bands. One of them is range, which is very useful for a lot of things. So what we can do, a little bit of an internal research and development project we did based upon some work that I've done in the past for combat engineers in the United States Army, is to apply 2D object detection and segmentation to these images. Typically, you've probably seen this in the past where these models can detect balloons and dogs and cats and make a little mask around them. We're doing basically the same thing here. What's interesting is this image can be reprojected back into points based upon that range value and some angular measurements that are maintained. It could be reprojected back into the point cloud. So when you do some pixel segmentation on this, where you're detecting all the pixels that make up a person or a car or the street or what have you, that could be propagated back to the point cloud very quickly. This is only really useful when you can apply it to, in the context of a moving vehicle. If you can apply this using what's called simultaneous localization and mapping, or SLAM for short. For those who don't know what SLAM is, basically it's an algorithm that allows you to move through an environment and map it at the same time. So basically, at each frame, your sensor has its own local reference system, which is pretty useless for creating a map. But what it does is the SLAM algorithm takes, it grabs features such as the corners of buildings, street lights, what have you, and it can recognize that on following frames. And so it's able to say, okay, I've moved 10 feet here, I've rotated to the left here, et cetera. So it's able to build that map. And so while we're doing object detection and segmentation on these objects, we can propagate that back to the point cloud while it's building the map, and it's quite useful. Typically, when we point clouds typically there's architectures out there like PointNet and PointNet++, which can take an entire point cloud and do detection on that and classify the point cloud that way using its own deep learning architecture. But the problem with that is it requires labeled point clouds as training data, which is extremely difficult to produce. This is much easier to produce. You can make use of automated object detection models like Segment Anything from Facebook to help you doing the labeling when you're training this for objects that you want to capture. So on the right here, this is just an image of the thing that the Ouster kind of brings to the table, which is the bottom portion of this, which is structured LiDAR data. You can see everything's nice and even, those pixels, and that's how we get those images really easily out of that sensor. As I mentioned, the sensor data can be both represented as a point cloud and a panoramic image at each frame, which goes into the SLAM algorithm. The initial research that we did, basically we're using You Only Look Once, which is a model architecture for object detection and segmentation, YOLO for short. And that's been trained on the cats and the dogs and the balloons and et cetera. And so on these data sets, the sample data that I just showed you, it's able to detect buses, cars, and people pretty well. So, and I'll show you an example of the final product for that. Oh, okay. This is the final product right here. Sorry, that went faster than I thought. All right, y'all have a good day.